All right, class, let's continue with section 1.5. So we talked about higher order derivatives, second derivative, third derivative, and so on and so on. So what do they mean? What sort of applications would a second derivative have? Even though we can go on finding derivatives, the third, the fifth, the 10th, they're not really all that important. The first derivative tells a lot about a function. The second derivative tells a lot about a function. After that, they become insignificant. Of course, in higher mathematics, definitely they're used more. But for our course, we will only concentrate on the first and the second derivative of a function. So one application, and even though this is an application from physics and it's really used a lot in a regular calculus course, I still brought it up because it's something we're dealing with pretty much every day. We're all moving places with a certain speed and a certain acceleration, if anything, right? You might increase your speed, that's a change in speed called acceleration, or you might decrease your speed, and that same thing, you're changing that, that's called acceleration. So one application from physics, I should say, of derivatives is the velocity and acceleration functions. So we're starting really with the position functions. It's called position functions because distance is really an absolute value of the change in position. You moved from here to here, you went a certain distance. Position is where you are at any point in time. And changing that position depends on the velocity, right? On how fast you are moving. So let S be a position function of an object at a time t. The velocity is simply the change in that position with respect to time. You all know, and you have talked about the fact that speed or rate or velocity, I'm going to call it, let's just say rate, is distance divided by time. So in other words, it's your change in position, right? So you went 5 miles, that's a change in position. You went from here to there. With respect to a change in time, it took you 5 minutes to get there, right? So you went from time 10:55 to 12 o'clock, to 11 o'clock, sorry. So that's exactly what a derivative is, right? The change in the function values with respect to the change in the x values, yes? So it makes sense that velocity, rate, and so on, called, is the derivative of your position function. Just to be, I'm kind of call it, I didn't really want to call it a speed because speed is really just the absolute value of the velocity. When you are taking a physics course or a calculus course, a velocity is a vector. So if you're moving in a positive direction, you are moving with a positive speed or with a positive velocity. But if you're moving in a negative direction, your velocity can also turn out to be negative. So speed is really the magnitude of it, how fast. It doesn't matter which direction you are moving, okay? So that's why I didn't quite want to call it a speed. And then the acceleration is definitely that change in velocity, right? You might be going faster and faster and faster. You might be going slower and slower and slower. That's a change in your speed, yes? And the change in speed or change in velocity, that's the derivative of it, and we call it acceleration, okay? So sure enough, if I'm taking the derivative of the velocity, which is the derivative of the position function, so the acceleration is really the second derivative. Okay, so that's what you really have to know. I wrote it here as well. Here it is. Let's say this is measuring the position of an object t seconds later. Let's find the velocity, right? The velocity is just the derivative of it. We've learned to find derivatives, so that's going to be 10t plus 3. Done. Now, the acceleration is the derivative of the velocity function. So, in other words, the second derivative of this one we're starting with. So the derivative of 10t is just the 10, right? So we found them, okay? So clearly, just as I said, we are, by the way, not only talking about velocity and acceleration when it comes to a moving object. Things can be, and you will see in the example, in the next example, we can be talking about a change in population. What's the speed at which a population's changing in time? Yes. What's the acceleration of that population change, right? So does it increase faster and faster? Does it increase slower? And so on and so on. So it's not, doesn't have to be about a car going left and right, or you walking to the kitchen and back, right? So anything that changes in time, right, that changes at a certain speed, okay, let's say. So let's say on the velocity, let's find this, v of 1, and interpret that answer. So velocity is the derivative of the function, acceleration is the second derivative. So we found them. Let's just say we want to find the velocity at 1, and what does that mean? So plugging in 1 into this velocity function, we're getting 13. So what does that mean? That simply means that after what? Again, remember, when you interpret these answers, you're starting with, if I would have plugged in a 2 here, I would have gotten a different answer. So that makes very much, or is very important, right, to what it is we're talking about. So after what? 1 second, yes, t is seconds later, so after 1 second, the object is moving at what? Or I should say the distance of the object, or the object is, how about this, the distance, because that's the y value of the object, is changing at a rate of 13, what's the y value, feet per second. Okay, so that's the speed, right, at which this object's moving. So many feet, right, that's the y measure, in so many seconds, right, or per second. Okay. What's the acceleration at 1? We already found the acceleration. The thing is, as you see, the acceleration is constant. So it doesn't matter what value you're plugging in. The acceleration is going to stay constantly 10. So what does that mean? That after 1 second, the velocity of this object is increasing by 10 feet per second per second. Okay, so the acceleration is a change in velocity, right? It's the derivative of the velocity function. What are the units for velocity? The units for velocity are feet per second, yes? So those feet per second will grow by another 10 feet per second every second. So next time, I'm going to get 23 feet per second, right? So in other words, if I were to plug in a 2 here, well, let me write this down on the side. What's v of 2? Plugging in a 2, I'm going to get 23, yes, feet per second, right, is the velocity of this object. So as you see, after 1 second, at 1 second, the velocity was 13 feet per second. Another second later, that's going to increase itself by another, what, 10 feet per second, right? So the speed is accelerating at a rate of 10 feet per second every second, right? So it's kind of what the, let me go back to this. It goes hand in hand with also the Leibniz notation, as you see here. when you take a second derivative, what happens with your x values? The derivative with respect to x with respect to x. So the x units are basically being squared. So in other words, 10 feet per second is the same thing as 10 feet per second over second is second squared, right? So these units for the second derivative, right, the x values are being squared, right, because it's per second, and then the next one per another second for the third derivative. Okay, so let's see this maybe with something else. So I'm going to look at the population of a city. So let's say the population of a city is given by this function. So you're going to have this many thousand people T years since 2000. So in other words, time is years after 2000, and P is the population of that city, and it's given to be in thousands. Okay, so first of all, let's look at the function itself. What does it mean to find the population in 2000 and the population in 2005? Now, the population in 2000 is how many years since 2000? That's 0 years, right? So when you plug in a 0 here, you're going to get what? 2,000 people. Okay. What about 2005? In 2005, that's 5 years later, right? So plug in a 5 in there. And put that in your calculator, and I already did that, and I am going to get 212,000 people. Okay? All right. So in other words, what? From 2000 to 2005, your population is increasing by about 210,000 people, right? That's, by the way, an average about of what? Let me grab a different pencil. On average, your population is increasing by how much? 212 minus 2 over 5 minus 0, it's 210 divided by 5, which is about 42,000 people per year, right? Okay. All right. So let's see if that might give us any clues for later. Now it says find P prime of 0 and P prime of 5 and interpret these answers. Now P prime means what? To find the change, the instantaneous. So remember, the derivative, which again we're going to find, is the instantaneous change in population. Okay, so first of all, what's the derivative of this function? So we've done a bunch of rules already. The derivative of this function is 2 times 3, which is 6, t squared, minus 3 times 2 is 6, t plus 7. Okay, plug in a 0, and you're going to get a 7. Okay, we're going to interpret this in a bit. Now the same thing, I'm not going to go, we already found the derivative. Let's plug in 5. So it's going to be 6 times 5 squared minus 6 times 5 plus 7. I plug that in, and I'm going to get 127. So what does that mean? That simply means, let's write it down. Initially, right, at time 0. So you can write at time 0, or you can say initially, i.e. in 2000. By year 2000, the population is doing what? Is increasing by how much? By 7,000 people per year, But by 2005, it's increasing how fast? By how much? By 127,000 people per year. Okay, so it's increasing faster and faster. Now, on average, about 42,000 people per year. However, what? It was starting slow, 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 and it went up way faster. Yes, on average, about 42,000 people per year, but it's not every year 42,000 people, right? It doesn't grow up at a constant rate. It was going slow, 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 and then it was going, so it was increasing slow, and then it started increasing way faster, right? All right, so an average, basically, let me just do this on the back. If you have, this is some cubic function, so really it's going to look like that a little bit. So on average, between year 0 and year 5, let's say, on average between year 0 and year 5, it might go up by what? 42,000 people per year, right? But that's just an approximation. That's if I go straight. However, what is really happening? The first year, it only went up what? 7,000 people, yes? Whereas in the last year of my 0 to 5, it went up by a whole lot more than 42,000 people per year, right? So an average from here to here, it just gives you what happened, like kind of the shortcut, right? About this much. Whereas an instantaneous rate of change, it gives you a better picture of what happens at that specific point in time, right? Okay, so in the beginning, only 7,000 people per year. By year 5, 120,000 people per year. So as you see, the change in population is accelerating. That means what? The population is growing faster and faster and faster. So that rate of growth is going up and up and up. And that's exactly what these mean. So the second derivative is really the same thing as finding the acceleration in the change of population. Right, so is that change in population going faster and faster and faster, or how are we changing? Yes, so that's what an acceleration is, the second derivative. Now, first things first, we have to find that second derivative with respect to any t, right? And as you see, the first derivative is right here. The function was up here, just to look back to what we're looking at, right? So the function, here's its derivative, and now here is its derivative. So the second derivative is 12t minus 6. Okay? So what is happening? Okay, let's plug in p prime of 0, the second derivative at 0. That's actually negative 6. The second derivative at 5, 12 times 5 is 60, minus 6 is 54. Okay, so what do these numbers mean? These numbers mean this, that by year 2000, or in year 2000, initially, right, the change in population was actually slowing down. So really, probably if I would have plugged in a 1 here, I would have gotten less than an increase of 7,000 people per year. Okay, so I'm just going to say this, by year 2000, the rate of growth in population is decreasing by 6,000, and it's decreasing because it's negative, the 6,000 people per year, okay? So it's the rate of growth, right? That is changing. That's the rate of growth, right? People per year. So that rate of growth is going to go down initially by about 6,000 people per year, okay? Per year, right? So I just said initially it's going to go down the first year by 6,000 people. And then by what? By year 2005, what's happening to that rate of growth? It's picked up back. So not only is the population increasing, but it's increasing faster and faster. So it doesn't mean that the population's not increasing. It's just not increasing as fast, okay? It is increasing, but slower than initial, right? So by 2005, the rate of growth is increasing by how much? 54,000 people per year. Okay. All right, so this is what this means, okay? All right, so that's what all of this is. Derivative, let me just grab another blank piece of paper. Well, I'll do it on the back. So again, by the way, gravity is an acceleration. Gravity is an acceleration, so our gravity on Earth, again, the units for gravity are feet per second squared, and again, it's because it's an acceleration, right? So just like people per year squared, that's an acceleration. So the units are being squared. What I want to give you to look forward to for chapter 2 is what does a second derivative mean for the graph of a function. That's how we will interpret this second derivative. So here I'm going to draw two graphs for you that are both, in fact, increasing, right? So this graph is increasing, is going up, up, up. This graph is increasing, is going up, up, up. But they're both increasing, or they each are increasing differently. And that has something to do with the second derivative. So what is a first derivative? The first derivative is the slope of the tangent line, yes? So here are tangent lines to your graph, and here are their slopes. And what can you tell me about these slope values? What do you think will happen to these numbers? Because these tangent lines are getting steeper and steeper, the slopes are increasing as well. And because the slopes are increasing, that means what? That first derivative is increasing. So if the first derivative is increasing, that simply means that the second derivative is going to be positive, right? Because you keep getting positive rates of change, yes, into the rate of change. Whereas here, when you draw your tangent lines, what happens to these slopes? The slopes are getting smaller and smaller. So the derivative values are getting smaller and smaller. That means what? The change from here to here, the change from here to here is a negative change, right? So the second derivative is going to be negative because the changes are smaller and smaller, so they're going down in a negative direction. Okay, so the second derivative will tell about what we will call the concavity of a graph. So if the second derivative is positive, the graph is turning up as it goes up. And if the second derivative is negative, the graph is turning down as it goes up. So this is called concavity. And just a little look ahead and what's to come in chapter 2. We'll be using the first and the second derivative to interpret what happens to the graph of a function, okay? Because that's what this is all about, right? Using the first and the second derivative to tell what's about to happen to the profits of my functions. The profits of my functions are going up, right? The first derivative is positive, so it's looking good. But look at that. The profits of my functions might be going up, but they're starting to slow down. So I'm going to be soon in trouble, and I might start going down, right? So my profits might start being on the downslope. So those are very important features, right? And that's what the first and the second derivatives are there to tell us about a function. Okay, so we'll continue this talk in chapter 2, in fact. All right.